Welcome, students. This is Gaurav Saxena, Assistant Professor at IIMT College of Engineering, Computer Science Department. So today's talk will be about a very famous open problem in computer science. This problem is called the famous $1,000,000 open problem in computer science. Why it's called $1,000,000? Because there are organizations like clay mathematical organizations which have offered $1,000,000 for the solution to this problem. So the title of this talk is the P versus NP problem. So let's begin. I'll talk about first of all what P and NP is, and then I will talk about what the real problem is. So the question is referred to as, like, if you ask the question, like Frank Wilczek, a famous physics Nobel Prize winner, was once asked that if you asked a super intelligent alien race one yes or no question, what would you want to know from the super intelligent aliens? And he got a Nobel Prize in 2004, and his reply was P versus NP. That basically contains the other questions, doesn't it? So that is the significance of this problem. So first of all, the first slide here shows you what is the significance of this problem. This problem is supposed to be very famous. It is referred to even outside the circles of computer science as a very significant fundamental problem. So this is a problem not just in computer science. It's a problem which has implications for other branches of knowledge also, because this quote is from a physics Nobel Prize winner of 2004. So let's talk about what P and NP are, so that we can understand why this Nobel Prize winner thought that P versus NP was such an important problem. So let's begin what P and P is. So this slide also tells you that what are the other $1,000,000 problems for which $1,000,000 are being offered. Of course, P versus NP is, which the talk is about, is of course the $1,000,000 open problem. Then there is Riemann hypothesis, Poincaré's conjecture, Yang-Mills mass gap, Navier-Stokes equations, Hodge conjecture, Birch and Swinnerton-Dyer conjecture. So all these are problems which are so significantly important for practical purposes. They're not just theoretical problems. They have practical consequences. And these practical consequences have made, not just in computer science or maths, but in all disciplines, have made people offer $1,000,000 for the solution of these problems. So these are the millennium problems and $1,000,000 problems, of which one is P versus NP, for which $1,000,000 are being offered if you can solve this question. Now, interestingly, all you need to know to understand P versus NP problem is something to be in the third year computer science syllabus. So all you need to know is third year computer science syllabus. And once you're in the third year computer science, you already have read design analysis of algorithms. You already have read automata theory. You already read theory of computation. So just design, and if you have studied design analysis of algorithm, which is normally in the second year, if you have studied automata theory, and if you have studied theory of computation, you know enough maths and enough computer science to understand P versus NP problem. And then you can even try a shot at it and become famous by winning $1,000,000. So let's look at the problem in more detail. Poincaré conjecture has been, successfully proven. So somebody has already gained the $1,000,000 for it. And let's look at some other problems, computer science, in a few slides. So let's talk about decision problems. Given an n, is it prime? Now, first of all, those who understand what is a decision problem. A decision problem is a problem which has a yes and no answer. So decision problem is a problem which has a yes or no answer. So given an integer n, is it a prime? It's a decision problem because the answer is either yes or no. Now, if you look at this problem, given an integer n, is it prime? Does it look like to you a very difficult problem, or does it look like to you easy problem? Now, one of the fundamental results in computer science is that some problems can be solved by computers and some problems cannot be solved by computers. Those problems which cannot be solved by computers are called undecidable problems. And those problems which can be solved by computers are called decidable problems. So this was one of the fundamental results obtained by computer scientists when they began the subject of computer science in 1930s. That itself has a very fascinating history. The history is that people like Bertrand Russell and Ludwig Wittgenstein and Frege were trying to base all of mathematics on logic and set theory. From their attempts to base all of mathematics on logic and set theory began the attempts to ask, is there an algorithm for mathematical problems? Do all mathematical problems have proofs? Is it true that everything that is true is provable? Is it true that all of mathematics can be done by machines without understanding the semantics? So all this led to these questions. And now we know, like the works of Turing and Gödel, Gödel showed that there are mathematical problems which are true, but which cannot be proved. Turing showed there are problems for which there is no algorithm. So let us look at this question. This is the decision problem because the answer is either yes or no. So let me ask you, does there exist an algorithm for this problem? That's the first question I'm going to ask you. The first question is, this problem is a yes and no problem. Does there exist an algorithm for these problems? So now you will try to come up with some algorithm. Now, normally people would say, okay, if a number is prime, then it is not divisible by any number less than it. So a trivial brute force algorithm will be to keep multiplying, keep dividing by all numbers up till n. So you begin with 1. You don't begin with 1 because 1 divides everything. You begin with 2. Divide n by 2. Then divide n by 3. Divide n by 4. Divide n by 5. And keep on going till you reach n minus 1. Then you divide. Obviously, n minus 1 will not divide n. So the question is, if you find any factor which divides n, then you know it is not a prime, it's a composite number. Then you will know it's a composite number. So thus we know the given integer, is it prime? The answer is that we can check one by all factors less than it. Now the question is, the algorithm exists. So it is not an undecidable problem. Undecidable problems means no algorithm exists. We have already shown for this problem an algorithm exists. So this is not an undecidable problem. So next question to ask is, can we make our algorithm more efficient? So think about it for a few seconds. We already have an algorithm. To check if a number is prime, we divide by all numbers less than it and check if it has a factor. Now the question is, if you are like trying to decide 10 is a prime or not. Now you divide by 2, you divide by 3, you divide by 4, you divide by 5, you divide by 6, you divide by 7, you divide by 8, divide by 9. Do you really need to divide that many steps, or can you make the algorithm more efficient? Now that is the question. If you make the algorithm more efficient, then you do not take that many steps to solve it. So the question arises, can you make this algorithm more efficient? The answer is yes. Now it's back. Yes. Sorry for the break. We are back. So I'll just share the slide again, and just a second. So yes. So we are back, students. So let's look at the problem we were looking at. So there is an efficient algorithm. You need not go all the way till n minus 1. You need to only divide till square root of n. Each n is an instance of the problem. So you can actually have an efficient algorithm for primality. In fact, there is an even more efficient algorithm discovered by Agarwal, Kayal, Saxena at IIT Kanpur in their BTech project. They discovered an algorithm which is not exponential in log n, which is polynomial in log n. So because the number size of the input is in log n. So this is about efficiently solvable problems. P is the class of those problems for which an algorithm exists and the algorithm is efficient. So define P as the set of problems which have efficient solutions. Efficient means runnable in polynomial time. So P is, for example, if I ask you to find the shortest path, if you find it in polynomial time, then I will say this problem belongs to P. If I give you a problem and ask you, given the solution, verify whether the solution actually is correct, then the problem is in NP because we are asking to verify, not to solve. So the difference between P and NP is the difference between solution and verifying. The only thing is P is the set of those problems which can be solved in efficient polynomial time. NP is the set of those efficiently in polynomial time. So you can actually refer to Google about Agarwal, Kyal, Saxena, and their paper primes is in P, which gave a more efficient algorithm than the one referred here. It was polynomial in log n bits, because even the brute force algorithm and even the square root algorithm is exponential in log n bits. So Agarwal, you can Google this paper, Agarwal, Kyal, Saxena, 2002. It's a BTech project, and it was famous for putting primes in the P category. So I hope till now you have understood what P and NP is. P is the set of those problems which have efficiently solved, can be solved efficiently in polynomial time. NP is the set of those problems. If I tell you the solution, then you can verify in efficient polynomial time. So that is P and NP. And that is the open question, whether these two sets are the same or the two sets are different. So let's say what mathematically is an algorithm. Now, for the first time, when you try to define what mathematically precise about what a recipe is. So Alan Turing, the great computer scientist, was the first one to mathematically precisely define what computation and algorithm actually is. He gave the concept of a Turing machine, which is the mathematical symbolism which captures the notion of an algorithm in a set theoretic mathematical manner. The first model for serial deterministic classical digital computer. Now the question is NP. So class of all decision problems for which a yes answer has a polynomial size proof that can be verified in polynomial time. So I hope I have made these points very clear, because the whole talk is about P and NP. So P is the set of those problems which can be solved efficiently in polynomial time, and NP is the set of those problems which can be verified efficiently in polynomial time. Right? I gave an example. If I ask you to find the shortest path, it's a solving question. If I give you the shortest path and ask you to verify if it's the shortest path, that's a verification question. So there is a difference between solving and verifying. So I hope you have understood the difference between determinism and non-determinism. Determinism means solving, non-determinism means verifying. So for example, look at this question. The question here is, does this big number have a prime factor ending in 7? So now solution. I'm asking you to find the solution. But if I give you the solution and ask you to verify it, then it's non-determinism. So you can see what is the difference between determinism and non-determinism. A problem is NP hard if by using a black box or an oracle, you can solve all NP problems in polynomial time. Now this is about the complexity zoo. Once you talk about algorithms, there are two things: correctness and complexity. So correctness means, is the algorithm correct? And complexity means how much memory and time it consumes, how much space and time it consumes. For example, in this case, NP hard, NP complete, P, NP, these are complexity zoos. These are definitions by computer scientists of sets of problems which have been defined according to certain criteria. For example, NP hard is a set of all problems. If you could solve the NP hard problem, you could solve all NP problems in polynomial time. Now, NP complete is a problem which is both NP hard as well as an NP. So these are definitions of complexity zoos. P and NP are obviously the ones which we are really caring about, but there are other definitions also in the complexity zoo. Let's give an example of an algorithmic problem. Given a graph G, does G have a Hamiltonian cycle? Now, if you remember computer science, what is a Hamiltonian cycle? Hamiltonian cycle is a tour that visits each vertex exactly once. Okay, and cycle means it returns to the origin. Now the question is, when you're asking, okay, so I think slide is not visible. I've created space. Now the slide is visible. Is it visible now? Yeah, okay. So now the question is, does this graph have a Hamiltonian cycle? So does this graph have an Hamiltonian cycle? Now the question is then whether a correct algorithm exists and an efficient algorithm exists for this question. That is the issue. So let's look at the next problem. Now obviously this is the solution. Now if I give you the solution, like this green line in green visits all the cities and returns back to the origin. It's a cycle which visits each vertex exactly once. The solution is given in green. That is the difference between P and NP. Determinism and non-determinism. Determinism asks you to solve. Non-determinism gives you the solution and asks you to verify. The question is whether the two sets are same. Now if you look at this particular diagram, it's very easy to see that how the different sets are diagrammatically defined. What is NP hard? What is NP complete? What is NP? What is P? All these problems have been given. So NP hard are all NP problems which are efficiently reducible to these, and NP complete are those problems which are NP hard as well as in NP. And P is the efficiently solvable problems, and P is the efficiently verifiable. Now, if you can see in this diagram, they have not enlarged P enough to cover all NP. They have not expanded P to cover all NP. They have actually created P as a subset of NP. That is the $1,000,000 problem. Is there an example of a problem which is in NP but not in P? Can you refer to the different problems in different sets? For example, in this case, matrix permanent and the halting problem, they are given in the set NP hard. And Hamiltonian cycles, Steiner's tree, graph 3 coloring, satisfiability, maximum clear are given in the NP complete. And factoring and graph isomorphism are given in NP. And graph connectivity, primality testing, matrix determinant, linear programming are given in P. So you can already see that different problems are given in different sets, and the P and NP sets are not shown to be equal in this diagram. In this diagram, they are not shown to be equal. If they were shown to be equal, then you would have actually solved the $1,000,000 problem. If you had actually shown that P is as big as NP, then you would have solved the $1,000,000 problem. So let's go to the next slide. What is the significance of this problem? Even Kurt Gödel, the most famous logician since the time of Aristotle, has said that if P equal to NP, then all the efforts of mathematicians can be replaced by machines. This was what he said in a letter in 1956 to John von Neumann, that this computer science problem is so deep that it actually has implications for fields outside of computer science. It has applications to stock trading. It has applications to algorithmic music making. It has applications to theorem proving. It has applications to whether mathematics can be done by computers or does mathematics need to be done by machines. All these are implications of this $1,000,000 problem, and that's why it's a $1,000,000 problem. So let's look at some more examples. What would be the consequences if somebody shows that P equal to NP and wins $1,000,000? So what does it mean that if somebody shows that P not equal to NP, what would be the implications? So not quite. Before we get carried away, are we first to ask whether P versus NP is even the right question? Like, is it the right question to ask? It is $1,000,000. So we have applications of Turing machines. I hope all of the students listening to this talk know what Turing machines are. Turing machines are the first mathematical capturing of the notion of algorithm. So they're the first way to capture algorithms. And if you dip two glass plates with pegs between them, make soapy water, then this is an NP hard problem. The soap bubbles forms a minimum Steiner tree. And this by the soap bubble actually solves an NP hard problem instantaneously. So there are ways to bypass Turing machines by laws of physics. People have tried to bypass the power of Turing machines by quantum computing, by applying weird physics, bubble soap physics, and thereby they have asked whether Turing machines can actually be bypassed by physics. And even people have tried quantum computers, people have tried relativity computers, people have tried to see the limits of computing machines and whether they can cross what the Turing machines define. Because ultimately, for an algorithm, correctness and complexity is everything. And because correctness and complexity is everything, ultimately it depends on a model. And the model is Turing machines. And can it be bypassed by the laws of physics? The next question. So this ultimate question is relativity can be done. Then again, we also look at the philosophy of computing. Like, who were the first people? The ancient Greeks were the first people to talk about the computers as a philosophical model. Like whether infinity can be captured in finite steps. Because after all, there are Turing machines that go on forever. There are Turing machines which try to solve a problem and they go on forever. So the Zeno's computer was the first to ask whether infinite steps can be captured in finite time. And if you look at this diagram, the diagram shows that each step is taking progressively less time than before. Step 1 is taking the maximum amount of time. Step 2 is taking the next amount of time. Step 3 is taking the next amount of time. And each step is taking half the time than the one which previous step is taking. So even if there is actually an infinite number of steps a Turing machine has to take, then also we can actually capture the notion of undecidable problems in a finite time. So that was Zeno's computer, which is the first philosophical way of asking whether even undecidable problems can be solved by bypassing the limitations of computing machines. Quantum computing is the next example people tried. when they try to deal with halting problem, decidable problems, undecidable problems, tractable problems, intractable problems, and P versus NP issues. Can quantum computing give us a way to solve these things? So quantum computing is actually using the laws of quantum physics to deal with these issues. The quantum, what is a quantum computer? Quantum computer deals with qubits instead of bits. Now you can Google what quantum computers are. Now normal computers deal with issues like bits, 0 or 1. Quantum computers deal with qubits. Qubits are basically about superposition of 0 and 1 state. So until the wave function collapses and you observe, till then the qubits exist in a superposition of 0 and 1. So that's what quantum computers are. And Peter Shor in 1994, it's an MIT scientist who actually gave the first quantum computer to show that factoring integers is in BQP, quantum polynomial time. This is also set in complexity zoo, and this has radical implications, just like the Agarwal-Kayal-Saxena algorithm, which I showed in the previous slide. Shor's algorithm also is a big breakthrough. And why are people so scared of these solutions? People are scared of these solutions because cryptography is based on the idea that it is easy to multiply but difficult to factorize. Many cryptography, RSA cryptography, for example, RSA cryptography is based on this issue. RSA cryptography is based on the issue that you can multiply easily, but factorization is hard. If factorization was not hard, you could break the cryptography and actually read mails which are encrypted. So that is why the algorithm which I showed, Agarwal-Kayal-Saxena algorithm for primality, and the quantum computing algorithm which I'm showing right now, which is Peter Shor's quantum algorithm, both had radical implications to what can be like whether cryptography is in threat. Because they say there is a book by Simon Singh called Code Book, which you can also check out, which says that the First World War, when the First World War happened, it was about chemists. Chemistry scientists were discovering chemicals which can be thrown at each other to kill the enemy. And then later on, Second World War was about physics, because people were developing atom bombs to throw at their enemies. If the Third World War happens, then it will be all about quantum computers, this P versus NP, cryptography, mathematics, bioinformatics, doing biology with computers, looking at DNA as a software, hacking the DNA as a software, taking coronavirus, making it more deadly by hacking the DNA of coronavirus, or making vaccines. So that is why people were investing $1 million into these problems, because these problems have radical implications. Then, of course, cryptography is in threat. And interesting is all these spies, all the worldwide spies are interested in this issue. Everybody wants to know whether this problem can be solved. And then again, the next issue is, can this have implications? Can quantum computers and Shor's algorithm have implications to P equal to NP or not? This is again a direction of thought which many people have explored. Proving P not equal to NP would be a start. So the question arises that if P and NP are not same, right now they're not considered to be same. If you take a survey and ask different computer scientists all over the place, why is P equal to NP, why P not equal to NP? As I said, if you show P equal to NP, you can do stock trading, you can efficiently, you can create music algorithmically, you can prove theorems algorithmically, and you can do mathematics, stock trading, and music making just by computers. It will be a big breakthrough for artificial intelligence. But if you ask most experts whether they believe P is the same as NP, most experts of computer science will say P not equal to NP. Even though Agarwal-Kayal-Saxena have given a P polynomial time algorithm for primality, still people still think that P is not the same as NP. Now, interestingly, I just showed you this diagram, complexity zoo diagram, which I'll just refer to again. Now, if you look at this complexity zoo, there is a set of problems called NP complete problems. Now the question arises, what is an NP complete problem? NP complete problems are NP hard problems which are also in NP. Now you know that if any NP problem can be solved efficiently, then all problems in NP are also NP. And those problems which are NP hard and also in NP are called NP complete problems. So if any NP complete problem you solve in polynomial time, then you have collapsed P equal to NP, and people have been trying different NP complete problems and solutions, but it's not working. So NP complete problems, till now, no NP complete problem has been given a polynomial time solution. It's not working. So it's just not working. And then, of course, the main reason why people believe P not equal to NP, Main reason, because otherwise the clustering of so many thousands of problems in two different categories would be an unexplained coincidence. So approximating 3SAT. 3SAT is an algorithmic problem, and whether it's satisfiability. SAT stands for satisfiability, and 3 stands for the number of clauses in the problem. So you can look at this problem: X or Y or Z, and X or Y bar or Z, and X or Y or Z bar, and all these things. Now you can see that in each clause there are three logical variables being connected. And if you the question is, can you assign zeros and ones to this formula to make it true? Can you assign zeros and ones to this formula to make it true? That is the question. And this question is again shown to be an NP complete problem. And 3SAT was in fact one of the first problems to be shown to be NP complete. And additional reasons for this: asymmetry of ignorance. Hierarchy theorems imply most pairs of complexity classes are unequal, so why not P and NP? So most pairs of complexity classes are unequal, because P and NP is not the only problem where we deal with determinism and non-determinism. The same problem can arise in space also. In fact, there is a theorem called Savage theorem, Savitch. You can Google Savage theorem, and that asks whether P space is the same as NP space, and it has been shown that P space is the same as NP space, thereby showing that these two complexity classes are the same. So P space equal to NP space was shown by Savage, but till now no other determinism and non-determinism class has been shown to be mostly they are unequal. So because of asymmetry of ignorance, people are betting that P and NP are also not equal. So the claim is, have we used physics instead of using computer science and maths? If we use physics, can we declare P not equal to NP a law of nature? In fact, there are computer scientists who are trying to base physics on algorithms. In fact, there is a computer scientist called Stephen Wolfram, who did his PhD from Caltech, one of the youngest PhD from Caltech. He tries to write a book called A New Kind of Science, where he tries to show that physics should be done with algorithms and not with equations. So once you do physics with equations, physics with algorithms and not with equations, the question arises: if physics can have a basis in algorithms, can the complexity issues have consequences for the physics of the universe? So P equal to not equal to NP is not just $1 million problem. It's not just a problem in computer science. It has applications to other fields. So I think the time has run out. So I'll just summarize that P NP problem is $1 million open problem, and anybody with a third-year computer science knowledge can actually have a go at it. I wish you the very best. I hope the lecture was informative and educational. I wish you the very best in solving this problem. Happy learning, and thanks for today. Thanks.